Hi everyone, this video for the diploma student who is preparing for the DCET diploma CET exam. The subject is analog electronics. This is presented by the Department of Electronic and Communication Engineering, Kerala Engineering College, Padua. The first question, in ideal diode model, diode in forward bias is considered as a dash. Is it resistor? Is it perfect conductor? Is it perfect insulator? Or is it capacitor? If you take as a diode, we know that diode is a combination of PN junction. So first side we have P type and another side we have N type. And forward bias means it is connected to the positive signal to the P and negative signal to the N. If it is something like that, when you give positive signal to here in the P type, we have the holes and positive carriers. So we know the rules. If same carrier together and it is attract each other, so positive is going this side and negative here negative. So this is again not attracted. So negative is going this side. From this, there is a small gap between PN junction because we are using as a semiconductor. So this gap is filled by this forward bias. So whatever signal we will give, because of filling this one, it acts as a conductor and we will get whatever positive given to this switch is closed. This particular operation known as a perfect conductor. So your answer is B. In ideal diode model, diode in reverse bias is considered as what? Resistor, perfect conductor, perfect insulator, capacitor. The same diagram what we discussed, if you take as a P and N type, you take P here and N here. Reverse bias means the P is connected negative and N is connected positive. So what happens? Plus here and N means it is a negative carriers, so it attract each other. So whatever the electron in the N side come this side. Same way in the P type, it has positive carrier. We are giving negative supply to that. It is attract each other, so it moves to this direction. So huge gap developed between P and N type. So this is gap makes that it is not conducting. So whenever gap between any two junction, so we call as an insulator. So our answer is it is a perfect insulator. Answer is next question. If voltage drop produced by a diode at forward bias in ideal diode model is equal to. So usually the diode we can call as a three type. One we can use usually silicon diode. Second one we can use as a germanium diode. And third one usually we use as a ideal diode. Ideal diode means it is actually not practically present. Whenever the calculation purpose we are using that. In SI diode, if I take as a PN junction, usually the gap between PN junction, the small area, it is 0.7 volt. If it is germanium you are taking, this area is 0.3 volt. If you are taking ideal, it is called as a perfect diode or super diode, and usually it is not present in practically. We consider this distance is 0 volt. So in this case we are taking as a ideal diode. So our answer is D, it is 0 volt. Next question, the current I through this circuit if you consider diode in ideal diode model. So diode we are taking as an ideal model, that means VD is 0 volt, and in this circuit we have resistor is 1 kilo ohm and input is 3 volt. The aim is we have to find what is the current on this part. So we can use the technique called as a Ohm's law here to find that. How to find this one? In an ideal diode model, the diode is considered as a perfect conductor in forward bias and perfect insulator in reverse bias. This is previous question. This is voltage drop at forward bias is 0 and current through the diode at reverse bias is 0. Since diode is forward bias current, we can call I is equal to V by R, where V is equal to 3 volt. So we call as a current is V by R, and from the Ohm's law, V is 3 volt and resistor is 1 kilo ohm. From this formula, we can say that 3 by 1. The 3 by 1 is nothing but it is actually we have 1 kilo ohm. Those reasons we are getting 3 milliamp. This is the answer of your current. So we can easily say that the answer is A here. The voltage Vout across the ideal diode, if Vin is 5 volt and resistance R1 is 10k is. So our aim is to find what is the voltage or Vout across the diode. So in this case, what are the given? We can see that the R1 is 10k given and Vin is given as a 5 volt. So from R1 and Vin, we have to find that what is the Vout. In an ideal diode model, the voltage drop at forward bias is 0 and current through the diode is reverse bias is 0. Since diode is reverse bias, no current flows through the circuit, so entire voltage appears on diode is 0. In this particular case, diode is reverse bias. So we know that reverse bias, it is a perfect insulator. So this case Vout we called as a 0 volt. So answer is whatever we are getting as a Vin, same thing we are getting in the Vout. So no conduction in this part. So we can call as the answer is A. The current I through the circuit I, if voltage V is equal to minus 3 volt. The current I through the circuit I, if voltage V is equal to minus 3 volts. In this circuit, the diode connection is actually the reverse bias. Why? Because we are giving V is equal to minus 3. When you give minus 3 over here, the negative voltage to the positive side, so this diode acts as a reverse bias. And in the reverse bias, there is no conduction. So whatever you will give as a voltage, we are not getting any current. So we are calling as a current is 0 amps. So answer is A. Again in this circuit, if current source I produce a current of 1 milliamp and resistance R is equal to 3k, then what is the voltage across the resistor given that diode is ideal? In this part, the diode is connected to the forward bias because the positive to the positive of the voltage source or current source, so it is called as a forward bias. Voltage drop at forward bias is 0 and current through the diode at reverse bias is 0. Since current forward bias, the diode it acts as a conductor, so current through the resistor is 0 to voltage is 0. Therefore, voltage across resistor is 0. So here we are calling as a answer is A. If resistance R1 is 10 kilo ohm, V2 is equal to 2 volt, V1 is equal to 3 volt and the diode is idle, then the current I through the circuit will be, in this case, if you are taken as this, here the positive is connected here, then again we are giving again here one more positive. So here diode is actually reverse bias because negative and this negative is connected, this negative and here, so it acts as a diode reverse bias. If diode is reverse bias, we know that voltage drop at reverse bias is 0. Since the diode in reverse bias, it can be considered open and no current flows through it. The effective voltage becomes 3 minus 2 is equal to 1 volt. So current is 1 divided by 10k is equal to 0.1 milliamp. So our answer is D. If resistance R1 is 10k and V2 is equal to minus 2 volt and V1 is equal to 3 volt and the diode is idle, then the current I through the circuit will be, if you consider the same circuit as a previous, but here in this case V2 is equal to minus 2 volts. So here we are giving as a minus 2 volt signal and here it is something called 3 volt. So and diode is reverse biased to the V1 because this is positive, but this is negative because of minus 2, so it is forward biased to the V2. From this case, we can say that since the diode is in reverse bias, it can be considered open and no current flows through it, then effective voltage becomes the voltage V2 forward bias, the diode, so in effect V2 vanishes and V1 is reverse biased to the diode, so it will not pass through the diode. Therefore, effective current will be voltage by resistance 3 volt divided by 10k. So it is 0.3 milliamp. So our answer is 0.3 milliamp. What will be the voltage Vout if VA is equal to 3 volt and VB is equal to minus 5 and the diode is ideal? In this case, VA we are giving as a 3 volt. 3 volt means it is forward biased to this diode, and minus 5 volt means it is reverse biased to the second diode. Our aim is what is the across in the Vout part. First diode in forward bias and second diode in reverse bias. So only first diode will pass the current. In this case, we are only passing the VA portion. So we are getting only 3 volt in the output side and no voltage from the VB side. So the 3 volt is the Vout, and in this case the B is the answer. DC average current of a half-wave rectifier output is dash, where Im is the maximum peak current of input. Average DC current of half-wave rectifier is Im divided by pi. Since output of half-wave rectifier contains only one half of the input, the average value is the half of the area of one half cycle of sine wave with peak Im. This is equal to Im divided by pi. Thus, this is calculated by area of graph of current. So, IDC is equal to 1 divided by 2 pi integration of I with respect to dx between 0 to 2 pi. This is equal, if we make as, we will get as a Im divided by pi. So, our answer is B here. DC power output of half-wave rectifier is equal to dash. Im is the peak current and RL is the load resistance. Average DC power of half-wave rectifier output is, we know that it is I by pi into R. Since power is VDC into IDC, where I into pi into V divided by pi, we will get as a V into I divided by pi. We know that V is equal to IR, therefore power is equal to I divided by pi into R. Average DC power of half-wave rectifier output is, we know that I divided by pi into R. So, since from this we say that VDC into IDC. If you simplify this equation, we know that I divided by pi into V divided by pi is equal to V into I divided by pi. So, from the Ohm's law, we know that V is equal to I into R. So, from this formula, we will get that the power is equal to, we will get I divided by pi into R. So, this is because of I square R, we are getting as a answer C, Im square divided by pi square into RL. Ripple factor of half-wave rectifier is, ripple factor of a rectifier is the measure of the effectiveness of a power supply filter. In reducing the ripple voltage, it is calculated by taking ratio of RMS AC component of output voltage to DC component of output voltage. So, we can call as a R is equal to root of 1 minus I divided by IDC. For the half-wave rectifier, it is called as a 1.21. So, answer is B. If the input frequency is 50 Hz, then ripple frequency of half-wave rectifier will be equal to what? The ripple frequency of output and input is the same, since one half cycle of input is passed and other half cycle is blocked. So, effectively frequency is the same. We are given as a 50 Hz, so answer also 50 Hz, it is B. Transformer utilization factor of an half-wave rectifier is equal to what? Transformer utilization factor is the ratio of DC output power to the AC output power, or we can call it as a AC rating of the secondary windings. AC rating is the product of RMS voltage across winding and RMS current through the winding, expressed in volt per amp. This factor indicates the effectiveness of transformer usage by rectifier. For half-wave rectifier, it is low and equal to 0.287. So, answer is B. If peak voltage on a half-wave rectifier circuit is 5 volt and diode cut-in voltage is 0.7, then peak inverse voltage on diode will be what? PIV is the maximum reverse bias voltage that can be appeared across a diode in the circuit. If PIV rating of the diode is less than this value, breakdown of diode may occur. For a half-wave rectifier, PIV of diode is Vm. Therefore, PIV is given as a 5 volt. So, answer is actually C. Next, efficiency of half-wave rectifier is how much? Efficiency of a rectifier is a measure of the ability of rectifier to convert input power into DC power. Mathematically, it is equal to the ratio of DC output power to the total input power, and efficiency we can calculate 40.6 into RL divided by RF plus RL percentage. It is maximum value is 40.6. So the answer is actually C. In half-wave rectifier, the input sine wave is 200 sine 100 pi t volts. The average output is. In this, we know that it is something A sine omega t. So here the omega portion it is 100 pi and A is 200. In this we have to find what is average output voltage is. Hence average output formula we know that amplitude divided by pi, that is here amplitude is given 200. So 200 divided by pi, if you simplify you are getting as a 63.66. So it is nearest to D. So we are calling as a the answer is D. In a half-wave rectifier, the input sine wave is 200 sine 200 pi t volts. If load resistance is of 1K, then the average DC power output of half-wave rectifier is how much? The equation of sine wave is in form of Am sin omega t, how I explained previous. In combining that, we know that here it is Am is equal to 200. The power we can calculate using the equation of sine wave is in the form of Em sin omega t. If you combining that, we know that Em is equal to, in this equation it is 200, and Em sin omega t where omega portion is 200 pi. In this case we require average DC power. So average DC power, the formula we can call as a DC power is equal to, we know that we have to take as a amplitude first. So we are taking Em. Previously I have taken A, that also holds good. Any amplitude name you can take, divided by, we can take as a pi 2 pi RL. So here the RL value is given as a 1K. Apply 1K here and 200 to Em. So if you simplify, you will get as a answer 4.05 watt. So this is nearest to the B value. So your answer is B. In a half-wave rectifier, the input sine wave is 250 sine 100 pi t volts. The output ripple frequency of rectifier will be. The equation of sine wave is in the form of Em sin omega t. On comparing equation, we know that W is equal to 100 pi, it is in radius per second. So we know that the omega is equal to is nothing but 2 pi f, where f is the frequency. So frequency is the given as 50 Hertz. Because we are using as an Indian standard AC signal, the frequency always remains standard as 50 Hertz. So we can take frequency of 50 Hertz. If you calculate, ripple frequency and input frequency always remains same. So if you take frequency is 50 Hertz, the remains in the ripple also 50 Hertz only. From this we can say that the output is 50 Hertz. DC average current of central tap full wave rectifier is what? Where IM is the maximum peak current of input. Average DC current is the average current in the output of the rectifier. For a central tap full wave rectifier, if a sinusoidal input is given, then output will contain only one half cycle repeatedly. So average current will be twice as half wave rectifier. So it's a half wave rectifier we discussed previous. It is Im divided by pi. It is twice here. So it is 2m divided by pi. It is called answer is A. Next, DC power output of central tap full wave rectifier is equal to what? Im is peak current and RL is the load resistance. DC output power is the power output of the rectifier. It is equal to V pi into I pi, or we can call as a VDC into IDC. We know that VDC for central tap rectifier and 2 VDC by pi and IDC for a central tap rectifier is 2 Im divided by pi. We also know that VDC is equal to IDC divided by RL from the Ohm's law. Hence, output power we can calculate from this. It is 4 Im square divided by pi square into RL, because the formula is the power is equal to VDC square by RL. So VDC whatever we are taken in the square form into RL. Previous session we know that VDC is nothing but 2 Im pi square, 2 become 4 square, Im square and pi square. So answer is the D. Ripple factor of central tap full wave rectifier is what? Ripple factor of a rectifier is the measurement of the effectiveness of the power supply filter in reducing the ripple voltage. It is calculated by taking ratio of RMS AC voltage to the DC output voltage. For central tap full wave rectifier usually we call as a 0.48. So ripple factor usually we are calling as it is the ratio of RMS AC. If the input frequency is 50 Hz, then ripple frequency of central tap full wave rectifier will be equal to what? Since in the output of central tap rectifier, one half cycle is repeated, hence frequency will twice of the input frequency, that is 100 Hz. Or in half wave rectifier, whatever input only output we are getting, full wave it is double of the half wave rectifier, so we can call it is 100 Hz. So answer is A. Transformer utilization factor of a central tap full wave rectifier is equal to what? Transformer utilization factor is the ratio of DC power supply to the AC rating of the primary winding. The factor indicated effectiveness of transformer usage by the rectifier. For a central tap full wave rectifier, it is equal to 0.81. With respect to the primary winding, 0.57. With respect to the secondary winding, that is double of that half wave rectifier, and the average value is 0.69. So answer is C. If peak voltage on a central tap full wave rectifier circuit is 5 volt and diode cut-in voltage is 0.7, then peak inverse voltage on diode will be what? To calculate PIV, it's the maximum reverse bias voltage that can be appeared across a diode in the circuit. If PIV rating of the diode is less than this value, breakdown of diode may occur. For a central tap full wave rectifier, PIV of diode is 2 Vm. Therefore, the PIV is 2 into 5 volt. We are calling as a 10 volt. So, answer is B. Efficiency of central tapped full wave rectifier is how much? Efficiency of rectifier, already we know that when you are converting rectifier AC to DC, how much efficiency will takes place. Efficiency always, it is output by input, so it is ratio of output power, that is nothing but we have output is DC and input is AC. It is usually expressed in percentage. For central tap full wave rectifier, if you simplify, it is 81.2%. So answer is B. In a central tap full wave rectifier, the input sine wave is 20 sine 500 omega t. The average output voltage is how much? The equation is shown as 20 sine 500 pi t, where 20 we are calling it is a AM or amplitude, 500 we are calling omega, so it is 500 pi. If you want to average output voltage, we know that the formula is AM divided by pi. 2 AM divided by pi. 2y because it is full wave rectifier. So AM is 20 into 2 we can call as 40 divided by pi. So 40 by pi is 12.73. So we can call it is answer A. In a central tap full wave rectifier, the input sine wave is 200 sine 50 by t. If load resistance is of 1K, then average DC power output of half wave rectifier is how much? Similarly, here if you take as a 200 sine 50, the 200 is again it is a amplitude and 50 pi is again is a our omega value. So the formula for DC power output, we know that 4 into AM divided by, we can call as a pi square RL. So 4 into AM is 200 into 4 we can call 800 and RL is 1K. So it is 1K of that into pi. So if you simplify this answer, you usually get 16.20 watt. So it is answer B. In a central tapped full wave rectifier, the input sine wave is 250 sine 100 pi t. The output ripple frequency of rectifier will be what? Again in this equation, if you compare with the AM sine omega t, AM is 250 and omega is nothing but 100 pi. So if you want here, we want ripple frequency. The ripple frequency is always as an input like that, but in this case we are talking about the which rectifier is the matter. So the output ripple frequency of rectifier we require. So we know that F is equal to W divided by 2 pi. From the formula, W is equal to 2 pi F. From this formula we can make, here the W is given 100 pi, so apply 100 pi divided by 2 pi. So pi get cancelled, 100 divided by 2 we can call as a 50. So here 50 Hertz is the answer, we get 50 Hertz here. This is for the half wave rectifier. Here we are discussing as a full wave rectifier. So full wave rectifier is a double. So if you are getting as a 50, you can multiply with a 2 because of double. So we are getting as a 100. This is what answer. So answer is C, 100 Hertz. Reverse saturation current of a common emitter transistor is what? Reverse saturation current is the collector current when emitter is open, circuited, and base collector junction is reverse bias mode. In this mode of operation, collector base junction act as a reverse bias diode. The current in this reverse bias junction is known as reverse saturation current. So we can say that the collector current when emitter is open circuit and base correct junction is reverse bias. So this case is satisfies. So we call answer is A. Next, reverse collector saturation current ICBO is what? Reverse collector current ICBO is collector base current when emitter is open. This is same as reverse saturation current in ideal but have a slight difference in practical. So we can call as collector current when emitter current is 0. So we can say that answer is A. Reverse collector saturation is greater than reverse saturation current because of reverse collector saturation what? Is it ideal or does not include leakage current or they are same or include avalanche multiplication current which is caused by the collision in collector junction. One of the reasons reverse collector current exceeds the reverse saturation current is the introduction of avalanche multiplication current in the base collector junction. This happens when high energy electron collides in the lattice. It creates more number of electrons and thus a greater current. Another major reasoning is the presence of surface leakage current following in the reverse collector saturation. So we can call that it is include avalanche multiplication current which is caused by the collision in collector junction. So it is answer D.